Hi everyone, welcome to a new edition of the HoloTube. And we're very happy to have today Niko Jokela from the University of Helsinki, who will tell us about a nicer view on holographic QCD. Please, Niko, go ahead.
Thank you. So yeah, thanks for the organizers for giving me this opportunity to give this talk. It's a great seminar series. I'm honored to be a guest speaker here. Okay, very good. So let me start by decomposing the title of the talk. So there's at least one word that you may not be familiar with, and this is the nicer. So I have here three figures. So my talk basically is composed into these three different objects here, and I'm going to try to describe those and how those fit together. So here on the left corner, you have if you wish, a phase diagram of QCD. So I'm assuming that many of you have seen something similar. And so this y-axis is temperature, and this is the chemical potential. And this is a very small figure, and that's intentional, because we don't actually know what the phase diagram is. So this is basically speculation what there is. So there's lots of work to be done to understand it better. But anyway, so high up here, at high temperatures, we expect there to be some quark-gluon plasma phase, deconfined phase. And when you go down in temperatures, you will land into the hadronic world, a confining phase. And we know that there is no phase transition here, so it's a continuous crossover. And so today we're interested in being on this mu axis, so the chemical potential, basically at zero temperature. So the whole talk is essentially at zero temperature. And there, well, what happens is that when you start increasing your chemical potential, at some point, the chemical potential is large enough in order to excite a baryon. So this is a quark chemical potential, so that's baryon mass divided by 3 roughly. And from this point onwards, there's finite density in the system. And I'm interested in neutron stars. So when I increase the chemical potential, I'm also increasing the density. At some point, there may be further transitions into, let's say, a deconfining phase, for example, quark matter if you wish. So you can speak your eyes and see what is actually written here. But as I said, we don't know what there should be. So we can speculate on that. Okay, so how is this connected with neutron stars? So here on the right, we have a cross-section of a theoretical neutron star. So we don't know, again, what's inside the neutron star, basically for the same reason that we don't know what's going on along this x-axis. So there are all kinds of models that tell us that there might be, all kinds of different phases inside. So there could be, let's say, quarks in the course of the neutron star, but at the very least, we have a rough idea what's going on close to the surface. So this is something called like a crust, and we have some idea what's going on in here. But something in the middle, that's sort of a question mark. The size of this object is around 20 kilometers in diameter, and it weighs 1 to 2 solar masses. It's a very heavy object. So something that is sort of on the verge of collapsing into a black hole. Okay, so this, we're finally getting to this NICER. So what this NICER is? So here's a figure of International Space Station, and this NICER is this small box here. So that apparatus, and so this acronym is coming from the Neutron Star Interior Composition Explorer, and it's supposed to probe what is going on inside the neutron stars. So this is really, like a game changer in this area, because now we have simultaneous measurements of mass and radii of the same object. So thus far we have only had, let's say, information about the masses of these very, these objects which are very far away and very small. So it's very, very, very hard to see. But with this X-ray device, it can actually figure out also what the sizes of these stars are. And it has to do with the fact that that they're looking at the pulsars. So pulsars are like lighthouses. So there's a beam that goes around, and it's sort of directed towards this this box here, and it can actually measure the arrival time. And from that, you can reconstruct what the size of this object is. So in 2019, there was a 1.4 solar mass neutron star that they were observing. It has this funny name, but in 2021, there was a higher mass neutron star that they observed. And this really actually brings in lots of new constraints. And that's what I'm going to discuss a little bit later. Okay, so there are already a few reviews on this topic. So people have been working on neutron stars via holography for some time already. So there are at least 2 reviews. So one where I'm also involved with, but there's this other one by Matti Järvinen, and so these 2 both are very long. So if you are tight in time, you should at least read Matti's review on this topic. Very good. So there's as I said, there are lots of different holographic models that you can pick from, and there's different amounts of information that have come out of all of those. And it doesn't really matter which one you pick, but I'm going to pick one that I've worked on very closely. But here's an incomplete list of different works in different models that you may have heard before. So some people know what Sakai Tsukimoto model is. So there are works in there looking at, let's say, quark stars, or even with baryons, and you can actually construct neutron stars completely out of holography. So these belongs into a category of, let's say, top-down in some sense. And there's also more phenomenological ones. So there's Einstein-Maxwell scalar theories. Many of you in the audience have worked on this in the context of condensed matter. They can also be applied in the context of QCD. I invite you to also jump into this. There was a paper yesterday on the hard wall model, and today I'm going to discuss this VQCD. So I'm not going to give you any references here. And apologies if I don't cite your works in the audience. I hope that we did cover everyone in the review. So, okay, so my outline today is something as follows. So I'm going to focus on equilibrium in the beginning. So I'm going to walk through how to construct these neutron stars and what to know about them. And then I'm going to briefly say a few words about out of equilibrium. So there's not too many works in that direction, and I hope that more progress will be seen there. And then I will end with a long outlook. So I might end my official part of the talk before that, and I hope that at least I will spur some discussions towards the end. And yeah, so please ask any questions during talk if you have any. Okay, so let me go into the equilibrium story. So let me just pick one model, and the one that I choose for this talk is it carries a name called VQCD. So this is not something that I have built. So it's based on many works by in our community. And for example, here is the one paper that you should look into, which is basically taking an earlier model called improved holographic QCD, and there you add quarks in this system, and this V stands for Veneziano limit. So that means that when you add quarks, you actually need to take into account the back reaction, and that's what this V stands here. So the limit that you take is that the number of flavors and the number of quarks are of the same order when you take them apart. And this is important because NF is of the order of NC in the neutron star context. Okay, so this is a bottom-up, and so I'm trying to do some phenomenology. So, but I'm still trying to follow string theory rules as closely as possible. And because this is a bottom-up, then there are lots of parameters. Okay, so in principle, there's an infinite number of parameters that I can throw in. And so what this actually gives us is an effective description of QCD. But because there are lots of parameters, I need to make sure that I will reproduce features of QCD as closely as possible. So I'm going to make sure that my model fits some known physics of QCD. And this works surprisingly well. So that's nice. Okay, so let me say a few words on how to constrain this to QCD. And so there's one thing that one needs to do is that so there are both qualitative and quantitative features that we need to match on to when we compare with, let's say, real world QCD, for example. Something that you can do quantitatively, for example, is that you may demand that when you are close to the UV of in energy, the coupling of the theory runs the same way that it does in QCD. Okay, and if you're a holographist, then you know that this is associated with how the dilaton behaves in the bulk. Okay, so basically knowing how the coupling runs in QCD, this basically fits you already the dilaton potential qualitatively. Okay, so that's something that you can analytically constrain at the U. At the IR, it's very hard to actually get something, you know, very precise, but you can get some features correct, like let's say some features of confinement and so forth. But there are still lots of parameters around, and those you can fit by to lattice data. So there's some quantitative numbers coming out of lattice QCD, and you can try to fit the rest of the parameters there. And that's something that has been done. So it has been done for the clonic sector in this paper here. And then we extended it into the flavor sector in this work from 2018. And here are some plots that you might be interested in. So here's an interaction measure as a function of temperature. So that's the energy density minus 3 times the pressure. And here's a barrier number susceptibility. So this is the derivative of the pressure with respect to chemical potential twice as a function of temperature. And this is actually something that actually constrains physics quite a lot when we want to now extrapolate to finite density. Okay, so you see that it fits this data very well. So maybe we are in good shape to actually extrapolate to finite chemical potential. So let's do that. So we now know that at zero chemical potential or small chemical potential, the model works quite well. And we can now extrapolate to finite chemical potential and ask what happens. Okay, so here what I have plotted is this is a temperature and here's a chemical potential. So this is a phase diagram in this particular model. And so at high temperatures up high up here, there you'll find this deconfined and chirally symmetric phase. So this is actually in the case when we have not allowed any bare quark masses. And then if you go down in energies, you actually find sort of a trivial phase. So this is a confining phase. So there's no black hole in the bulk geometry. So this is what happens. So there's a first order phase transition between the two. And as you know, this is not as what happens in QCD. And there's of course a good reason why this is so. I can discuss that later if you wish. Here, there's a new phase appearing. So this is this blue one. And this is a phase where we have baryons in the game. So many of you have worked on baryons in holography, and you know that they have to do with wrapped branes on some internal cycles. But this is there are no sort of internal directions in this particular model, and but you can still think about them as a solitonic and topologically non-trivial solitonic solutions in this theory. And they happen to appear in this corner of the parameter space. And this is precisely where you expected them to actually pop up. Okay. So this is the phase diagram of this holographic model. So it looks sort of okay. And the numbers are also reasonable. So This is roughly where it was supposed to happen. Okay, very good. So, but this VQCD, I don't trust it at very low densities, because I mean the nuclear matter phase, so this baryonic phase, I don't trust it that much when I'm close here. This is because here the densities are getting very small, and the approximation that we use to generate in this baryonic phase, it's called a smearing approximation, and I expect that to actually break down. So I'm only expecting it to be a very good approximation around here, but not in this region. So what I want to do is actually to switch to another model here, and there I want to use traditional nuclear matter models, effective field theory descriptions. Okay. So I'm going to postulate a certain. So there's a hand raised.
Hey, Niko.
Yes.
So about the last slide, why do you say 400 is large and 300 is small? Is that what you were saying?
Oh, but these numbers.
Yeah.
So this is okay. So this is a chemical potential. So chemical potential is probably not something that is intuitive, but if you translate that into density, then it's you gain better control of what's going on. So
okay.
So here we are. The densities are getting few times the nuclear saturation density. So the nuclear saturation density roughly corresponds to a density of a nucleon. Okay, so when the density is getting larger than the density of, let's say, a nucleon, then what happens is that these baryons, they begin to overlap. Okay, and when the density increases, then you might expect that the approximation that I used for these baryons, which is that I smear them over all the transverse directions, that might be a good approximation. Whereas when the densities are very small, so this is around here, then you actually begin to see individual baryons. So it doesn't probably make sense to think that the smearing approximation is a good one.
I see. Okay, and I guess, yeah, maybe a bit related question. So I guess assuming that at high temperature you can use perturbative diagram, like perturbative computation, high chemical potential, you can use perturbative computation then. So like this one is like, you probably have some cutoff where there is a weakly couple somewhere on the right, I guess. Or are you not going to talk about that?
That's going to be the next one.
Okay, thank you.
All right, very good. So this is part of this slide. So let me just say that. So that perturbative region that Nick commented on, it has to do with this orange region here. So this plot is the pressure as a function of energy density. So you can think about this as let's say density, if you wish. So roughly the same x-axis as in the previous one. So if I go to the right corner, I'm getting into more and more dense system. So here we know that perturbative QCD it works quite well. So when the densities are very large, PQCD is something that we should trust. Okay, so that's here. So the holographic model that I have now are these curves here. And you notice that they actually do go through this band where PQCD is trustworthy. So that's a consistency check, if you wish. But what I'm advocating here is that when I'm going down in energies, first of all, there's going to be this first order phase transition that you noticed in the previous slide into a nuclear matter phase. And then at some point, the densities are getting smaller and smaller. Then I should begin to suspect that my holographic model is not good. And that's where I actually want to switch to a traditional nuclear matter model. It's this point here. And I try to do it as continuously as possible. So we did it here. We didn't have too many parameters left. So there were basically one parameter that tells us at which density we do this for a given model. And then it just sort of turns out to be a second order phase transition. But you can do something a little bit more sophisticated, but that's what we did. And so in here, we are then following some traditional models. And that traditional model that I show here as an example is called APR. So this is Upmal-Pandre-Ravenhall. That's a very well-known nuclear matter model. Okay, so you notice that there's a transition here that's sort of a continuous, and then there's a first order phase transition and the quark matter phase. Okay, but I don't only match onto one particular nuclear matter model. I choose a family. I choose everyone that is sort of physically still viable. Okay, basically the ones that span this blue band. So this blue band is something that is generated by chiral effective theory. So all the nuclear matter models which are physically sensible should go through this one. And I picked all the models that basically span through this region. So basically I have control of all possible ones. Okay, so there are two regions here. There's the blue one and there's the red one. And we notice that this red one is significantly smaller than the blue one. And what this says is that there is so this red one is the one that comes from constraining to meet with holography, and it is telling us that there is predictive power when I use this holographic model. Yes. So there's a question about Sven.
Yeah. So just to clarify, so the contours of the without and the with holography, they depend on how you can vary the equations of state. So you do the inverse map from the nicer constraints back to the equation of state. Is that right?
Okay, so that's a very good question. So there are right. So there are these bands. So this band. So this is basically the reason that I'm changing the model in nuclear matter. So I'm choosing all the possible ones that there are. So that's you can think about as a parameter if you wish. So there's a different models that I allow. But there's a little bit of a free parameter range in the holographic side too. And this has to do with the fact that when I did my lattice fit, that's not constraining enough. So there's a little bit of a leeway there. And that also generates a bit here. So in combination, there's this red one that is basically all that I can say. So I cannot say better. And then when I implement nicer results, I will tell that in a bit. I'm not there yet. Okay, so there's one thing that you can, for example, extract from here, which is what is called the speed of sound. So this is the derivative of the pressure with respect to the energy density. Okay, so if you look at this one, so you have all kinds of different curves here. So what this is telling us is that the pressure at the given energy density. So this is basically a measure of how much the matter opposes compression. Okay, and this is quantified by a number called the stiffness. And it's not really the pressure as a function of at the given energy density, but actually its derivative with respect to the energy density. Okay, and that is sometimes called a speed of sound. So if you are doing hydrodynamics, they are equivalent, but they are not quite the same. Anyways, so this is the speed of sound, and it tells us how stiff the matter is. So I'm plotting here the speed of sound as a function of the density, and this is now in the units of this nuclear saturation density. So this is something intuitive. So when we are at number 1, this means that the density is the same as the density of a nuclear. And when I increase the density, then you have some idea what's going on. And you notice that the speed of sound, it goes in high values, higher than conformal value. And at some point, there's going to be a first order phase transition into a quark matter phase. So we jump into this quark matter phase. So here too, there are different bands. So there are all the, let's say, physically viable ones and the ones that are left after constraints. Okay, so that's roughly one example of what you can extract. And it's sort of interesting that this figure that comes out, that bears resemblance to other stuff. So for example, if you look at nuclear matter models, by this group, Freeman Weise and Bruce Weise. So they were looking at their nuclear matter model. They did some functional renormalization group stuff to extract what happens to the speed of sound. They also generate a band if you wish. So here's a small inset. You can see that this is the speed of sound, and you notice that it goes above the conformal value. You can also do similar game at high densities for quarks. And that is done here by this group, Otto, Oertel, Schaefer. And there's a band coming out. And then you notice that there's going to be, a similar kind of a jump that happens here. And that's no accident, actually. This DD2, that's actually one of the curves that we also have here. So that's something that happens. But what is sort of funny is that these numbers where this happens, they are sort of comparable. Okay, so let me now go to this to the neutron stars. I will get closer to this nicer also. So how do we build a star? Okay, so that's the topic now. So now I'm going to leave aside holography. Okay, so you can now go back to our four-dimensional Minkowski space, and we can think about solving Einstein's equations given some sources. Okay, so we have a four-dimensional space-time. So here's a metric ansatz. I'm trying to find solutions which are spherically symmetric. And one solution, which is a Schwarzschild solution. So this is a solution when the energy momentum tensor is 0. Okay, but if there's some matter around, you have a non-zero energy momentum tensor. And you know that the entries here, this is the energy density, and then there's a pressures on the left of the diagonals. So I want to solve this Einstein equation in the presence of this energy momentum tensor. And I'm assuming that I have a perfect fluid. So that's why I wrote down a very simplistic energy momentum tensor here. The Einstein equations, they are very simple. So they are written actually down here. Okay. So there are, let's say, 3 of them if you wish. So you can actually just forget about this and focus on these 2. Okay. So there's a differential equation for the mass as a function of the radius. And there's another differential equation for the pressure as a function of the radius. So there are 2 equations, but there are 3 unknowns. So there's the mass, energy density, and pressure. Okay. So in order to solve this system, one needs to know what is the relationship between the energy as a function of the pressure or vice versa. Okay, so that's why I told you that you need to compute this relationship from somewhere, let's say holography, and then you can actually go and solve this system. So this is actually very easy to solve. So you see that this is an ordinary differential equation, so you can do it. Okay, so if you have this relationship between the pressure and energy density, there's a one-to-one correspondence to the solutions of this system. The solutions of this system is a curve. It's a curve in the mass radius plane. So each point of this curve corresponds to a different star. Okay, so if I have a small star which has a mass of this one, this curve tells me what the radius is. And there's actually a one-to-one correspondence between these 2. So what these points here mean is that if I'm sitting at this point, this round one. So what happens is that when I'm beginning to solve this system, I'm solving it in such a way that I'm solving it from the interior. I start from the interior of the star with some core pressure, and I integrate outwards, and I try to find a solution for which the pressure vanishes. Okay, so I know I only need to know the curve below this point. Okay, so that gives me these stars. And this one corresponds to another one, and so on and so forth. But there's a little bit of a catch here. So if you want to just work out your equation state, you also need to make sure that, especially if you're doing holography and you know what your microscopic degrees of freedom are, you may want to make sure that your matter is charge neutral and it's in beta equilibrium. So this has to do with the weak processes, and it's equilibrated in that sense. So it's not complicated, but that's something that you need to keep in mind. Okay, so what we do now is that I'll take my EOS that I provided and I plug it into those equations. So those are this TOV, Tolman-Oppenheimer-Volkov equations, and I will obtain this mass radius relationship. Okay, so that's an exercise that one can do. And so here's a plot, mass versus the radius. And you recall that I had these bands for the pressure and energy density. So those transform into bands in this plane. So now I have bands in the mass radius plane. Okay. So this blue one would be the band without input from holography. But if I make use of holography, I get a significantly smaller band. And there seems to be there is still predictive power. So there are some constraints that I have implemented. So now I can say something here. So one of them is that I have assumed that my equation state has to be stiff enough such that my mass radius curve hits this 2 number here. Okay, so I disregard all those equation state that it does not happen. Okay, because I know that there are neutron stars of that mass out there. So my equation state better to be stiff enough in order to get those stars out. Okay, so that's one thing. And there's actually another hidden constraint here, and it has to do with getting rid of these ones. And so on this side, and that's input that came from LIGO and Virgo. So the LIGO and Virgo, what they provided us was information about what is called the tidal deformability. So this basically tells us a little bit about the squeezability of a neutron star. When a neutron star is in a gravitational field with another neutron star, it will begin to deform. And the reason that this effect was not seen in LIGO, that will give bounds, upper bound on this deformability. And that is sort of interesting that it works the other way than this limit. So this high mass neutron star limit, so it actually gets rid of these kinds of mass curves. And we are left with this. Okay, so that's what we have implemented so far. So one thing that to notice is that, yes, so there's a question.
Yes, sorry, in the risk of sounding silly, so and on the previous slide, I'm sorry to go back. So the one-to-one correspondence, I think, is mathematically correct, but I think it's not point to point, because I think on the right-hand side it should be like if you take a path, there's a one-to-one correspondence between a path on the right-hand side to the point in the left-hand side.
Yes, yes, absolutely. So that's so I said that here, if you have this round point, I need to know everything that is below it in order to construct this star.
Yeah, but I could take many paths to the round point, right? So I mean, it needs the whole trajectory, so it's like a Wilson line. I mean, I could take many paths, so it's not just following this curve. So if I draw another curve, it would be,
I see. Okay. Very good.
I mean,
but
so
okay.
maybe at the risk of sounding silly.
No. That's okay. So okay. So if I'm an ideal world that I know how to compute this curve. Okay. Let's say I know how to solve QCD. There's only one curve. Okay. So then for any given point, there is one.
That's an assumption.
Response to that. Okay. Maybe that's.
Nico, you want him to repeat the last thing he said, or he just said it was an assumption? Or something? Maybe.
What was? Can you repeat the last point?
No, I just mean that there is only one curve is an assumption. So in principle, you could have many curves in the right-hand side. So it depends on how you calibrate your model or what you assume about your model.
Yes. Okay. Very good.
If you recalibrate your model, you could have different curves on the right-hand side, and then that would give different points on the left.
Yes, you're exactly correct. And that's actually something that I tried to say, but I probably didn't do a good job. But this is precisely what I tried to explain here, that I don't actually have one curve, but I have a family of curves in equation of state. And that translates into a whole band here. So I don't actually get one curve, but I get a whole band in MR plane. And I think that we agree here, but I did a poor job in explaining.
Thanks. Sorry.
All right, excellent. So very good. So so what we have found is that these curves are actually cut here, and if you actually look at the endpoint of these curves, you can actually notice that it actually corresponds to the point where there's the first order phase transition between the holographic nuclear matter and holographic quark matter phase. And that seems to be quite universal, and maybe this is something that well, you should look more closely in other models. But in all the models that I have now seen, this has happened in holography, that that somehow the deconfinement phase transition seems to set the maximum mass of a neutron star. That seems interesting. Okay, so one other thing is that in holography, it seems that the neutron stars with larger radii, those are preferred. Okay, so now finally into this nicer. So this puts further constraints into these bands. So here on the right, I have the mass radius plot again. So there are all these bands, and then there's the equation of state. But let us look at this one first. So what these nicer measurements did. So recall that there were two stars that were observed. So there was this one that was in 2019. So the mass was around 1.4 solar mass stars. So what you get out are these probability distributions, these ovals here, if you wish. And those don't constrain too much. So it didn't constrain too much. But what did actually do a lot here was these ovals from last year. So these are for this neutron star, which is of the order 2 solar masses, and they were able to figure out the radii to some, to some window here. So the reason that there are two ovals is that there are two completely independent teams in the NICER collaboration. There's one that is mostly based in Maryland, and the other one in Amsterdam. And they have a completely independent ways of doing the analysis, and that's why you get two different kinds of results here. So to how to implement these constraints on this MR, that's quite well, that would be very technical to explain. But there's one way to get some intuition, is that you can actually sort of translate it into a radius. So if you look at 2 solar mass star, you can translate it into a lower value on the radius of that star. Okay, so if you do that, then you can draw these bands here. So here there are these two different colors. The black one is the one that corresponds to the analysis of the Amsterdam group, and the blue one is the one with that corresponds to the analysis of the Maryland, and that's more stringent. Okay, but you notice that this blue band is still there. It didn't go away. Okay, so we try to implement all the constraints there are coming from astrophysics, and our model is there and alive. Okay, so, and there is still predictive power. And you can ask, so what can we now learn? So if you now go back into the equation of state, you can see that it's severely narrow. It's much smaller than previously, but it is still there. So you can actually, if you take this model seriously, you could say that, well, this is the way that QCD matter should behave in this region. Okay. So I've highlighted here this red one. So that's one particular curve that seems to be, a good representative of this family, and that's something that we have carried through elsewhere also. Let me repeat that these NICER results, these are compatible, that there are no quark matter cores still. There's only holographic nuclear matter. Okay, but but since we don't do experiments in lab where we could actually test whether QCD matters behaves like this, what we can at least do is that we can hope to get more data from gravitational waves. So there could be further mergers of neutron stars, and they will emit gravitational waves, and we can capture them, and we can try to see what our model predicts for those. Okay, so one can, for example, compute what are the gravitational wave peak frequencies. So when you have two neutron stars and then they merge, they emit gravitational waves, and there are some peak frequencies. So this you can do either by actually doing numerical simulations. Those are very costly, but you can do it. Or you can actually use some universal relations. So there are relationships in the literature. So people have done lots and lots of numerical simulations, and they have found a way to represent them in such a way that they're sort of quite insensitive to the equation of state. And from those, you can actually compute predictions for these peak frequencies. So I have here two plots. So this is a frequency at the time of the merger as a function of the mass. So I have picked here a case where I have two neutron stars which are of the same mass and they merge. And this is the frequency at the time of a merger. And here are our predictions for that. If the companion that comes out is not a black hole, it's not a prompt collapse into a black hole, there could be a hypermassive neutron star form, and there could be further peaks in the gravitational wave spectrum. And here is one. This is what is called the F2. And so here are some predictions for what that might look like. So if there are some actual measurements of these peak frequencies, one could go and check how well this model works. Okay, so as I said, there are numerical simulations. They are costly, but they have been done even in VQCD for some case, and also in this paper yesterday by this group in this hardball model. Okay, so let me now comment something. So I mentioned that there are no quark matter cores, and this is something that that is, you might have heard in the news that there's evidence for quark matter cores in neutron stars, and we say that that's not the case. So this seems to be in tension with this interpretation, and this is, for example, discussed in this paper, and they say that there are sizable quark matter cores in massive neutron stars. And what they say is that they actually find that that if you have a hadronic star, they would need to have very high speeds of sound in order not to have quark matter cores. But our speeds don't actually go that high, so it looks like there's some sort of tension going on. But that's not actually a contradiction. What is going on is that in our case, the nuclear matter phase equation of state behaves differently to the assumptions that they make in this paper. Okay, so it looks like that the holographic matter behaves qualitatively differently than any other models there are in the market. Okay, and this is something that is quantified by a number called gamma. So this is called an adiabatic index. Okay, so this may be a good sign for holography. So our model, so this predicts low gamma. It turns out that Sakai-Sugimoto model, it also yields more gamma. So you could ask, oh, well, maybe this is also something, you know, I don't know, I don't want to say universal, but maybe this happens in many of the other holographic models too. So here's a challenge for you, so you can try to check this in other cases. So this looks like that, well, maybe if they keep not seeing quark matter cores, maybe that's a good signal for holography. But of course, there are also some examples of non-holographic nuclear matter models where they also have found that gamma goes to very low values. And I have only found this one. But this is not, if there is one, there has to be an infinite number of them, because you can always sort of slightly deform your equation state a little bit, and that's another model. And this is called the masquerading effect. Okay, very good. So let me, so I have got a little bit more than 10 minutes. So let me flash through the out of equilibrium. So this is a little bit more recent. So why is this important? So we know that that holography is not only good for computing equilibrium stuff, but it's also good for computing out of equilibrium. Something where, let's say, lattice QCD in particular has challenges. Okay, so let me think about our star again. So here's my cross section of our star, and so this is a figure from this very nice review by Schmidt and Sternin, where they basically label the regions of a neutron star where different transport properties or transport coefficients could be relevant. And if I'm interested in, let's say, very dense regions, perhaps hadrons or quarks, then these are the labels that I'm interested in. So if I'm interested in, for example, computing something that I know how to compute, let's say, bulk viscosity. So this is something that many of you have computed in many models. So you can ask, so well, maybe this is relevant for neutron star physics, and that turns out to be the case. It's not clear how and when these are going to be relevant in let's say, merger physics, but at the very least, there has been some studies already when people have done simulations beyond perfect fluid approximation. Okay, recall that when I constructed my neutron star, I assumed that I have a perfect fluid. So this is basically the state of the art. So people haven't been thinking about going beyond that, perfect fluid. Okay, and when you're actually doing these simulations, there is lots of things to, it's very complicated process. So adding, non-equilibrium stuff, it's getting more and more, complicated. In particular, because there are also numerical viscosity effects. But at least there is some stuff that has been done, and it has been identified that maybe bulk viscosity at least is useful. So that's why we went and tried to compute these things. Viscosities, other viscosities, those are also relevant for instabilities. I can discuss this later after the talk if you wish a bit more. And also the conductivities, these are relevant when one is interested in neutron star cooling. So when the neutron star, let's say, they merge, the temperatures rise, and then they will begin to cool down, and then you need to know what are the thermal and electrical conductivities. So these are the things that you are interested. Okay, so this transport, this is very actually challenging to analyze, as you probably know. So this equation of states for dense and cold QCD matter from the perspective of perturbative QCD, this has very large uncertainties. Okay, so what happens is that you actually need to be around, I don't know, 40 times the nuclear saturation density and above, then you can trust PQCD. But the core densities are at most, let's say, 10. Okay. So if you try to extrapolate from PQCD down to core densities of a neutron star, your uncertainties are blowing up. Okay. So this is the state of the art current. And the analysis that goes into this PQCD, that's many loop order. Okay. And you need to systematically begin to increase the number of loops to get better and better control. But about transport, this is the situation is even worse. The only known result is at the leading order. It's basically a free theory, a kinetic theory from which you can extract first principle results for these transport coefficients. And this was done 30 years ago. So there's certainly room for improvement. Okay, but we know that in holography, these things are easy to compute. So what we do is that we fluctuate the metric and all other fields and just read off these transport coefficients. Okay, so I know that, well, you all know how to do this, so I'm not going to explain, but let me just point out that, for example, when you want to compute what is the shear viscosity, it is given by entropy density divided by 4 points. So that still holds in at finite density. So that's one thing that you may wish to know. But anyway, so we computed all these things in a class of models. And the class of models that we focused on, so now I finally show you one action. So here's an action that we focused on. So here on the first line, so this is the governs the clonic physics. So there's the Einstein-Hilbert term, and there's a scalar. You can call it a dilaton if you wish. And then there's a matter part, or the flavor part, and you notice that there's NF here, there's NC. So this is down by NF over NC, but recall that I'm considering this in the Veneziano limit, so they should be the same, or of the same order. But we also did this computation for another model, this probe D3D7, and if you're interested in. But anyway, so you can compute these transport coefficients for this class of models, and we did that also at finite frequency. But for the usefulness, we also provided attractor formulas. So you know that many of the quantities, let's say even this eta over eta, is given by data at the black hole horizon. Similar formulas can be also written for the bulk viscosity and also for these conductivities. So they can all be written in terms of horizon data. So we provided those formulas. So if you have a model that fits into this class, you can just read them off. And in principle, you can also expand this into in a power series, and you might get some information about the Einstein-Maxwell scalar theories. So that also belongs into this family if you wish. So one thing that if you're actually planning to do this computation, what you can do is that you can supply all that information in an online data bank. So this is called Compose. So there you can deposit your equation of state together with, let's say, transport properties if you wish. So that's something that people actually who do numerical simulations, they actually go into this site and they download the equation of state and they do the simulation. Okay, so if you are planning to do this, then I suggest you to also upload your equation of state into that data bank. Very good. So let me just flash this slide. So here's a plot of the shear viscosity as a function of temperature, and on the right I have a bulk viscosity as a function of temperature, and there are different curves, and the different curves correspond to different chemical potentials if you wish. So here you notice that there are these curves that are holographic results for quark matter, and this is the PQCD result, this green band. And you notice that it's qualitatively different behavior. Okay, and so if one is trying to do numerical simulations, one should really think about whether or not one should think about using holographic result. It's at least in this region, the PQCD is way beyond its applicability. So maybe there's something that you might actually gain from using holographic results instead. So here's the bulk viscosity, and here you notice that there is no PQCD results around because they are very small. So the leading order contribution actually vanishes because the quark masses are very small. So we also have plots for these conductivities if you are interested. Okay, so let me summarize. So my message here is that this gauge gravity duality, combined perhaps with other approaches, is a useful game to study dense QCD. And using, for example, this EQCD with some simple approximations, many details actually work very well. So we had a precise fit of lattice thermodynamics at small chemical potentials. And then when we extracted the physics to finite densities, it looks a very reasonable thing to do. We had a simultaneous model for nuclear quark matter. So this is something that is quite rare. And what we obtained is that we obtained a very stiff equation for nuclear matter. So that was also sort of a good news. I discussed a little bit about the predictions. So we sort of predicted an equation state for cold matter, a QCD matter. I discussed a little bit about the transport, for the quark matter phase, and discussed a little bit about the properties of neutron stars, and in particular gave some predictions for gravitational wave spectrum in neutron star mergers. Okay, so one could then ask, so this holography, it's it's a tricky game, and it's not always clear where to use it further. And you can ask, well, is all the simple things done? And that's not the case. So there's lots of actually to be done, and I hope that some people in the audience take up the challenge. So I have identified here different regimes where one can actually make progress with, well, probably not too lots. Yeah, you probably don't need to work too much to actually make some significant advances. So one of them is to have different quark masses for the for the flavors, finite temperature. So this is something that you might think that it's easy. It's not. Finite magnetic field. This is discussed nowhere. Nobody has discussed any finite magnetic field effects in holographic neutron star context, nor about inhomogeneous or mixed phases or anisotropy. So advances in any of these topics actually is important in neutron star context. So I actually have slides on all of these, but since I run out of time, so let me stop the official part here. So thanks a lot.
Thanks a lot, Niko. Very nice. Now we have time for questions. I see many people around, so please don't be shy, just ask. I see David has his hand raised. Just ask.
Okay, thank you. Nice to see you, Niko. I have a question about your discussion of transport coefficients.
Yes.
So you mentioned there is this difference between the holographic result and the perturbative QCD result and so on. But my question is the following. Suppose that you could compute in QCD, in real world QCD, at any density, the transport coefficients, all of them. My question is, would this be relevant at all? Because these are the microscopic QCD coefficients, which will have some natural scale of the order of the Fermi, but the gradients in neutron stars are of the order of the meter. So the product of the gradient times the transport coefficient is absolutely, it seems to me, please correct me if you disagree, completely negligible in a neutron star situation, unlike in a heavy ion collision where the two scales are the same.
Yes, so thanks for that comment. That's a very important one. Yeah, I don't think that I disagree what you said. So this is something that where you have also assumed that your ground state is homogeneous, and so it could be that that there could be, larger gradients there when you're considering inhomogeneous phases. And this is actually something that is expected when you go to very high, dense regions.
You're talking about like crystalline phases, you mean?
Yes, and we know that, well, in particular, okay, large NC QCD, we also know that it's not going to be a homogeneous ground state. So it's going to be a chiral density wave and so forth. But in QCD, I don't know what to expect. So
maybe one comment is that in that case, I would expect the inhomogeneity scale to be, again, or something set by the QCD scale. But at least in the absence of this sort of symmetry breaking, I think that when people talk about viscosity being important, it's always an effective viscosity given by these Orca or inverse Orca processes, all these things, which is not the microscopic viscosity that I think one would be computing with holography.
yes. So yes, absolutely. So in the context of neutron stars, when they are discussing these viscosities, they're really discussing the effective viscosity.
Yeah.
But this is not QCD. So I actually have a formula. So there's an effective viscosity that is coming from weak physics, ultra-weak physics, and it's written down here. And that's something that one actually needs to consider real QCD, if you wish, the one where the masses of the quarks are different.
Mm-hmm.
But the physics has to do with weak, ultra-weak sector. But what is going in is the QCD physics. So one needs to know what are the, let's say, the susceptibilities of these quarks, individual quarks, in order to get something non-trivial there. But absolutely, so it's the weak physics that is sort of the relevant.
Yeah. Okay, thank you.
More questions? No more questions?
So
Yes, you can.
just to comment on David's question, I think it was a great question, but it's just as a counter example, you could think of like what happens in turbulence. So it's not necessarily true that the scale only, if the physics is local, that would be only acting at that local scale, but like in turbulence, it could be like in a neutron star that there would be a transfer of energy scales. So it's not totally clear until we understand what's going on at strong coupling that what happens at QCD scale wouldn't affect the meter scale.
Thanks.
Yeah. So just a comment. And to Niko, I want to say, so sorry for interrupting you during the talk, but it was a really nice talk. I enjoyed it. It was very nice. So as I'm officially employed in the math department, I'm sorry for being a little bit nitpicky about the definitions between your diagrams. So I'm sure it was very nice. I just want to make to be sure that like all the curves in the EOS, they are actually like, it always depends on models, right? So if, for instance, if I would improve your model, in principle, that curve on your EOS could change, right? If I could improve your model somehow. Yeah.
Yes.
So it's not like I can't say that I excluded it. I mean, we don't even know how much that curve would. So I could know how much is the confidence level on the right-hand side of the NICE experiment. But then when you do the inverse map, it becomes sort of fuzzy because you are assuming the US, and how much I would change over there. It's a differential equation, so it becomes difficult to see how much happens over there, right? I mean, from a physicist eye, your diagram is most surely very good, but just like philosophically speaking, it's hard to see what the error bars would do over there, right? I mean, you draw all the nice, you drew it for different values of your model, and that's
yes,
shows what happens.
Yes, I think that I understand what you say, and I agree. So let me go back to maybe, for example, in this plot. So what I'm trying to use information from here, and I'm trying to say that, well, let me try to map that onto what happens on the left-hand side. So you can think about this as an inverse problem. But I'm actually not doing an inverse problem. I'm doing a direct problem here because I have all these curves, and I'm just reading off what happens on this side. I'm not trying to reconstruct my curve on the left-hand side.
Okay, but the problem is the constraint is only on the right-hand side. And if there's a change in your model, like if I could improve your model, that would change the curve on the left-hand side.
Yes, that's right.
And so what if somehow I added an operator to your model that would increase the speed of sound by 10% or maybe 15%, that could maybe make a big change to how the curve will look on the left, even with the bounds of the right.
Absolutely. Yes, that's right. But you can always do that, but then you can ask, so does it still fit with, let's say, lattice QCD that I started with?
Yeah. So, but there is some gray zone where we don't know what would happen in principle. I mean, so for perturbative QCD, we know what happens, and in nuclear physics, we know what happens. But in the middle, we are a bit fussy about what exactly happens.
Yes, that's right. So we don't. Well, this is what happens in this particular model. So there are some freedom that is still there. So in principle, I don't know what that freedom is.
Yeah,
and
that is what I'm trying to say.
Something could happen. So
yeah. Yes. Okay. Thanks again and I enjoyed your talk very much.
Oh, thank you.
Very good.
Well, but let me now ask. I mean, there's freedom, but if you stay within holographic QCD, I don't think you can do anything you want in the left-hand side of this picture, right? You can. Otherwise, you would get no bounds at all.
Okay. Well.
So, if you believe in your model and you did the fits to, I don't know, lattice or whatever then you don't have infinite freedom, I guess.
Okay, so there's not infinite freedom, but that there are lots of approximations that has been going in.
Yeah.
And you can ask, so how good an approximation have you made? For example, for the nuclear matter phase, I assumed that my baryonic phase is something very simple. So I said that I just mirror these individual baryons in all the transverse directions, and I pretend that that's a good approximation. I don't know whether it is, but it seems to be because at least it looks reasonable and things like that. Okay, but it's not sort of a systematic way of doing it. And then similarly, you take any model, holographic model, you always go into the limit when NC is large. You have no idea what happens when you extrapolate to NC equals 3. So that's always with us. So we don't know what are the moving parts.
Okay.
And this is also sort of connected with, I put here quotation marks, even though all these models are, top down, and you would imagine that you know what happens. That's not really the case. In all of these cases, including my papers, there are uncontrolled. So if they're extrapolated in the regime, they are not really applicable.
Okay. Okay. We've had some questions, but as always, there is time if somebody has more questions. Otherwise, let me remind you that then I will open the floor for informal comments or discussions if there are one after I stop the recording. So no more questions. Okay, then let me thank Niko again. This very nice talk. and remind all of you that next week at the same time we have Jan de Boer with us. So thanks again, Niko.